Now going back to the residue, which is you already mentioned that if you have an isolated singularity, and especially a pole with a certain order, so you have to be defined outside the singularity away over angular region. Then you have this Lorentz series. Then a sub n is your a to the minus one power. The coefficient of the z minus c to the n minus one power is called your residue. Okay, and that is what it is. Okay. And that is that include all the different order, the first order, simple pole, or second, third, or order, or essential singularity, as long as isolated singularity and not branch point. And you have Lorentz series over each one of them. Then you can find you have c sub 0 and c sub 1, and you can circle those out and you find Lorentz series very close to it. Then then you found the function the residue over an angular region surrounding it. And but the idea is this function is expanding over c sub 0, so you have this a sub n. But if you have another singularity, then the expansion will be different. So I don't know what you call it. They don't call it a sub n. You already have a sub n, you call b sub n. Okay. You get one. You expand over another singularity, then you have different set of coefficients, and the b minus one coefficient will be the residue of this singularity. Okay, and so on. You can have many singularity. Okay. And okay. Then once we define that the residue theorem is just to say that if you integrate, you have like more many singularity, and then you want a loop integration, see around the region that is analytic except isolated singularity within it. Okay, so integrate around C in the positive sense, obviously we always do that. Let's see, dv that is equals to 2 pi I sum over all the residue. And maybe you want to be specific, then you define this as C sub 0, C sub 1, C sub 2, and so on. Then it's 0, 2, well, and right? The residue of C sub n. All the singularity, right? And so that is a theorem, but to see that is actually quite straightforward. Right? The idea we want to use the Cauchy integral theorem that if the loop is the function is analytical within the loop, then the integral is 0. You want to construct a loop that is that the loop will not contain this singularity. So basically, you want to deform your contour to basically get those singularity out of the loop. And to do that is like take a detour. We did that quite a few times. Anywhere is fine. It's just conceptual. It's not doesn't have to be practical. So going around a detour from C and go to a singularity and go very close to the singularity and go around it. But when you go around it, obviously you're going to positive, I mean clockwise direction, right? It's different from the original sense of rotation. Right? Originally, it's a counterclockwise. You go into it, you go a clockwise direction because you want to get back out. If you go counterclockwise direction, go back out, you go into the wrong direction. Okay, go in the clockwise direction and go back out. Uh, these two lines will be infinitesimally close to each other. Then you continue, and then you do the same thing for other singularity. Right? In and out, and go clockwise. In and out, go clockwise. Right? Now, after you do that, the deformed loop now has no singularity. Right? After you do that, all the singularity are outside the loop. Then you can use residue, Cauchy theorem, Cauchy integral theorem to say that this loop is zero. So this loop now the new loop is originally C that we want to calculate first. But then we deform it. So we have these parallel segments, but they are pretty much cancel each other. You don't actually need to consider these two because the function f is analytic and then obviously it's also continuous. So when you get to infinitesimally close and it's not multi-value, then the two line integral will cancel. Okay, so you don't need to consider all this strict line going in and out. All you need to consider is all these little circle. And this little circle is very close to the singularity. So when they are all loop integrations, say there's a little circle C sub 0, C sub 1, C sub 2. So basically, and then they're going clockwise in the negative sign. Negative sum over all the residue M. And then loop C sub M of the same function, obviously, same function. And that equals 0. Okay. And then obviously, because it's 0, then you can say that the original integral is just equals this sum. Or you can, right now you can say it's equals to this. Right. Now all this, because C sub M, all these loop are very close to the singularity, and so that on each of these circles, the Lorentz series apply individually. You have different Lorentz series over this different range, different circle. So one Lorentz series, the other Lorentz series, and other Lorentz series. So for you look at just one of them, the C sub M. The Lorentz series obviously is just sum over n from minus infinity to infinity a sub m, a sub n for the m pole, right? And then C minus C sub m to the n power. This is F of the DC, right? And obviously you know how to do that because these are just constant. So all you have this power function. We did that before, right? What would this be? There's many terms. The n from minus infinity to infinity. So when you do the integration like that, going a loop very close, say C sub m is here, going around a little circle, the C sub m is centered at G sub m with a radius like very small delta, right? And then you can apply the Lorentz series But I'm saying term by term, what is this? We talked about that before. It depends on n, obviously, it depends on n. What is it for different n value?
N is minus 1, 2 by I,
Yeah,
and 1.
it's all zero, right?
Yeah.
All zero. All zero except n is minus 1. Okay, so that would be equals to uh, so a 2 pi I times a minus 1 for the n whole, right? So finally, we got 2 pi I sum over n and a sub minus 1 for n. Okay, so that's basically the residue theorem.